Hello everyone, Harry here. Welcome to Scrap Science. About a year ago, an idea came to me. You might even call it a dream. I was thinking about melting down metals. I own an electric furnace that is capable of reaching around 1100 degrees Celsius. And for the purposes of melting down metals, that temperature can melt most of the metals you might want to regularly melt down. Aluminium, copper, zinc, anything like that is easily melted in my furnace. One issue though is that very occasionally I've had the need to melt down a metal with a higher melting point. It's really not very often that I've wanted to do this, but for example, in the past I've wanted to melt down maybe a small amount of cobalt into a little bead, or maybe a small piece of manganese metal into the form of an electrode to use for an experiment. And of course, my electric furnace is not able to do that. The limitation there is not actually the crucible that we use to melt things down in. This is a graphite crucible and can handle very, very, very high temperatures. Instead, it's the heating element itself in the furnace that really can't handle going much hotter than that. But graphite itself is conductive, so if you could get a power supply set up that passed current through this crucible itself, you should be able to effectively get it as hot as you want and melt down any metal. Graphite has a melting point that is higher than any metal, including tungsten, the highest melting point of the metals. So in theory, if you could pass current directly through this crucible and put some tungsten in it or any metal, the setup should resistively heat up this crucible and melt down the metal that's inside it. Now, of course, the amount of current that you'd need to pass through this thing to actually melt tungsten or even steel or even something like copper would be enormous. All right, I can't think of a way that I could set up a power supply to do that. However, if we got a smaller piece of graphite and, drilled a hole in it to make a crucible, which I'll be doing later in this video, we should be able to conceivably make a power supply that can resistively heat up that amount of graphite and melt down any metal that we put inside it. For me in particular, who only wants to melt down very small quantities of high melting point metals, this is kind of ideal, and I'm hoping that this will work. Hopefully it's clear what my plan is. If it's not, it will be clear once I actually start putting things together and you can see exactly what I'm doing. But for now, the first step is to actually make our high current power supply, and to do that, I've got a microwave oven transformer that I'm going to be modifying into a high current AC power supply. Out of all the things I've ever done on this channel, working with a microwave oven transformer is by far the most dangerous thing. And sure, I'm going to be destroying the high voltage output and turning it into a low voltage output. Nonetheless, microwave oven transformers routinely kill people who mess with them or try to do projects with them. And so to stay completely out of that, while I'm working on this high current power supply, I'm not going to explain what I'm doing. A bit later, we've put together the power supply that I want. All right, I've replaced the 2000 volt winding of the microwave oven transformer, which was a lot more difficult than I thought. This is all the copper that came out of that. It was an awful job, but we got there in the end. I've remade a new coil, just one turn of the thickest wire that I could buy at JCar. Not sure of the exact gauge. I could read it on the wire, but I don't really care. Anyway, the main part of this idea is this in the middle. This is a graphite rod that I have just shorted the output of my winding of the microwave oven transformer with. The idea here is that the entire output of the microwave oven transformer right now, which will be probably no more than a volt, is just directly connected across that graphite rod, no current limit. It will draw as much current as it can due to the resistance of the graphite rod itself. Graphite isn't all that conductive, so we're probably not going to get like hundreds and hundreds of amps, but we do need to start somewhere because I need to know how much current a setup like this will draw. Okay, with everything set up, I'll talk you through what I've got laid out here. First of all, we have a current clamp that will measure the amount of current we're getting out of our winding. This will just tell us the AC current in amps. Then I've got this multimeter here that we will use to check the voltage across the graphite. From a bit of prior testing a few minutes ago, I know that the unloaded output of the microwave oven transformer is about 0.6 volts. Hopefully, when we turn it on, that entire voltage will just be completely shorted across the very small resistance of the graphite, drawing hopefully a lot of current. And powering up. Already you can see we're getting nearly 27 amps. Additionally, if I hold the microphone close to the transformer, you might be able to hear the classic 50 Hertz hum. Anyway, let's now check the voltage across this thing. Yep, you can see exactly the same thing I measured before, 0.6 volts AC. Anyway, let's turn this thing off. And did our graphite get hot? Well, yep, that I can tell. That's very, very hot. Now, of course, just making the graphite too hot to touch is nowhere near the amount of power that we would require to actually melt metals. We'd need to get the graphite at least red hot to do that. So clearly, we're not putting enough power through it. However, there are very easy ways to increase the power that we're going to put through this graphite. Number one is we can shorten the length of the graphite that we're heating up. This will do two things. It will decrease the resistance that we're applying the voltage over, and also decrease the amount of graphite that we need to heat with the certain amount of power that we're running. So say if I decrease the length of this graphite by a factor of 3, just take a third of this length, we should be able to get a third of the resistance and then 3 times the power. Per gram of graphite, we're getting 9 times the power. That's in theory anyway. Additionally, if that's not enough to push enough power through this piece of graphite, we can also quadruple the power again by running another loop through the transformer. This will double the voltage and also double the current, and as such, it will increase the power by a factor of 4. Anyway, one thing at a time, I'm going to go off and shorten the length of graphite to 1/3 of what it is now, and we'll see what that does. All right, take 2 with a shorter graphite rod. Whew. All right, 90 amps. That's impressive for 0.6 volts, I would say. If I measure that voltage again, still 0.6. I'm very impressed that the contact resistance is low enough to allow for that much current, actually. Now, trouble is, I don't have a thermal camera, so I can't really tell exactly how hot it's getting. It's obviously not getting red hot, which would be nice. If I touch this wire, this wire's getting... Nah, not really getting warm. So I assume we've got nearly 60 watts of power just directly heating that graphite. Okay, well, 100 amps, but still not hot enough to melt any significant amount of metal. I can also see the insulation of that wire, and that wire is melting just a little bit, which I'm not particularly happy about. So, good thing that we've stopped it here. Having now rewound the microwave oven transformer, short test a couple of minutes ago told me that we have about 1.6, 1.7 volts on the output now. So a little bit nervous about what's going to happen here. I imagine we're going to get a couple of 100 amps, probably, at least. Hopefully I've made the connections properly here. Seems pretty solid. Watch the current meter as I turn on the transformer. $220 amps, that's a lot. Hey, there, it's getting red hot. Look at that. Okay. Gonna turn that off. I imagine already, yeah, these are getting hot. Skipping forward, I haven't really done very much here. Basically, I've stripped back these wires a little bit more to make sure that we can radiate some of that heat that's going to be generated between them before we have a chance to actually melt the insulation. I'm hoping that this length will be around enough to do that. And I've got this kind of stupid little drill press thing here. And what we're going to do with this is we're going to take our graphite rod, we are going to drill the core out of this rod, and then we're going to use that as a mini crucible in our setup. Gross. And ultimately, the setup is really quite simple once we've put it all together. I've got the microwave oven transformer on its side. Our wires come out. We've got our makeshift mini graphite crucible that will just sit vertically like this. We'll put anything we want to melt in that tiny hole. Another connection will be made on the top, and hopefully when we pass enough current through it, the outer walls of that graphite crucible will get hot enough to melt whatever we want to melt. As a first test, I have some small amounts of copper wire. I want to know that it melts copper because I already have a furnace that can melt copper, and if we can't melt copper with this thing, then it's really not worth using. If we can melt copper, we'll start moving up in terms of metal melting points to test what we can actually do with this. And test number 1 to try to melt copper, starting now. And I might try stopping it there. We'll let that cool and see if we were able to melt that copper. Well, yeah, look, it didn't melt down into one bead, but we definitely did weld those copper wires together. So I think that's clear indication that we are getting to above the melting point of copper. And as such, before we ruin our mini crucible too much, I'm going to move on to the next highest melting point metal that I have. I have here some tiny flakes of manganese metal, which is a little bit higher in terms of melting point than copper is. So our next test is going to be trying to melt this stuff. Manganese test number 1. I've made the crucible even smaller this time to encourage even more current to flow. Starting now. Wow. Okay. Gonna give it a few more seconds. Oh, yep, the graphite's just caught fire. I don't know if you can see that. I'm gonna turn that off right now. Once again, partial success. We were able to melt together a few small portions of the manganese we put in our mini crucible. See, it's melted into this kind of slightly round bead. However, there were some manganese flakes in there that did not join the overall bead that we were forming there. Again, likely just a problem of me not running the thing for long enough to get everything to melt down, but it does concern me slightly to run this for more than like a minute because the wires do get very hot. The insulation does start to melt even though I've cut it all the way back here. So we're going to take that partial success as confirmation that we can reach temperatures above, what is it, 1250 degrees? I don't exactly remember. The melting point of manganese, anyway. As one final challenge to see what temperature we can actually reach with this thing, I have a very small amount of nickel metal. Nickel test number 1, starting now. Starting to hurt my eyes to look at, but we're going to push on. Okay, I'm calling it there. To be honest, nothing is coming out of there, which means I think we may have actually melted nickel. Sadly, I'm going to have to break this open to get it out. But I think that's quite promising. And honestly, breaking it open, there it is. That is a tiny bead of nickel that we melted down from a piece of nickel foil. I was about to end the video there. Melting nickel was going to be the crowning achievement of this video, but then I remembered I have an even better metal to melt down, and that is titanium. Titanium, of course, has an even higher melting point than nickel. So what I've done is I've got a new crucible. We've got our piece of titanium foil that I'm just going to drop down in there. Whoops. Harder than it looks. There we are. I'm going to put this back into our power supply, and then as the actual end of the video, we're going to try to melt titanium. Titanium test number 1. Let's go. It's even more current than last time, nearly 400 amps. Already getting red hot. Let's see how hard we can push this one. I think I'm comfortable leaving it there, turning it off. There we have it. Slightly disappointing result. We were not able to actually melt our titanium foil. You can see here, the titanium foil is still intact. It got significantly more brittle and a bunch of it kind of fell to pieces, but we did not melt the metal. Whilst being slightly disappointing, this does narrow down the temperatures that we can reach with a setup like this. So seeing as we were able to melt nickel but not titanium, we must be able to reach temperatures within this range. I reckon if we could get one more turn of the secondary winding here, that would more than double the power that we're putting through an equivalent resistance. So no doubt that would be nice, and we would probably then be able to melt the titanium. Sadly, I can't fit another winding of this particular cable. So either I've got to get a bigger transformer or a cable that's, slightly smaller, but not so small that it starts to limit the current itself. Regardless, I think this was a pretty big success. We were able to melt nickel metal, and that's something that I've never been able to do before. And with all that said, I think we've kind of come to the point of the video where I feel like I need to justify why I think this setup is, a good way to melt small amounts of metal. Sure, we can melt a small amount of nickel in it, but we could also melt that nickel by just shorting the output of this transformer with a piece of nickel, and the amount of current that runs through the piece of nickel would probably melt it. The reason I think this method is really nice is because if, say, we had, instead of a piece of metal to melt down, like a metal powder, say you've just done a platinum group metal extraction and then you've just precipitated a platinum group metal out of solution and you've ended up with a very high melting point metal powder. Normally in those cases you're working with very small amounts of metal, so this kind of thing would be really nice to melt down platinum powder back into a bead. Second, if you've got a somewhat reactive metal that would kind of react with oxygen, or you'd lose a whole bunch of your metal due to the formation of oxides as you melt it down, this kind of setup could conceivably be used under an inert atmosphere. So you could get a little needle with some argon and just blow some argon into the top of that crucible. Would need some changes to the design, but at least with this kind of setup, it's very achievable. Third and final use that I can think of for this thing is if you want to make a pellet of like an oxide material. So say I wanted to sinter together a whole bunch of aluminium oxide into the shape of, the pellet that would fit into the core of this crucible. All I'd really need to do is to just pack a whole bunch of oxide in there and then heat it up, and hopefully that would sinter it into a pellet. That's something that I may want to do in the future. I've got a couple of plans that may require that kind of thing. But anyway, those are just some of my ideas so far. It's not a solution to every problem. Maybe tell me in the comments if you can think of any other things that I might be able to use this thing for. Nonetheless, maybe I'll come back in a future video with some improvements to the design and try to melt titanium again. But for now, I'd like to get back to some electrochemistry for the next video. So see you later.